Well, in fact, since we're here, I think let's follow through with the probability of a type 2 error here. So for the type 2 error, um, given that this is our test, so let's make an example here. So find beta, probability of a type 2 error. Now, this is the probability that the alternate hypothesis is true, and yet the test tells me it's not, to take the null hypothesis. So generally I have to pick a p in the alternative hypothesis. So you got to give it something. So and it really does make a difference, because if I pick p near 2/3, then very high chance of a type 2 error, right? It's right on the line. But if I pick p very high, like if p is 1, there's a 0% chance of a type 2 error. So I want to pick something and kind of keep that in mind when I make a type 2 error. So just because maybe it's a reasonable thing to pick, let's pick p is 3/4 again. So say p is 3/4. So this is the probability type 2 error given p equals 3/4. So this is h. So that's all I need to say. Okay. Well, this is for each of these cases. So for the case when k equals 12, b p equals 3/4 this is the probability that anything except 12 happens. So this is the probability that y star less than or equal to 11 given p equals 3/4. So could you tell me the binom command in this case? So the binom command would be, this would be equal to, this is 11, right? P binom 11, 12, 3/4. Come over to my R here. Wow. 0.97 about. So, look, very unlikely, and it makes sense, right? It's very unlikely, and in fact, it surprises me it's not even smaller. If it's 3/4, the chance that the chance that 11 or fewer, the chance, right. Okay, now this makes sense. If it's 3/4, what's the chance I make a type 2 error? The chance I make a type 2 error, given that it's 3/4, if k is 12, this means the probability that y star is 0 through 11. So it's everything except the probability that y star is 12. So it's actually 0.97. I guess there is actually a 0.03 chance that they're all going to be yes at 3/4. Maybe that makes sense. 3/4 is pretty big. Okay, let's do it for, so that's the probability of a type 2 error is k is 12. For k equals 11, b p equals 3/4 is equal to the probability y star is less than or equal to 10, given p equals 3/4. This is equal to p binom 10, 12, 3/4. And I just plug it in here into R. And it should come down. Yep, comes down a lot. So this is about equal to 0.84. Okay, so if the actual probability of a vote for A is 3/4, and I want to only conclude that there's at least 2/3 majority if it's greater than 2/3, then there is a 0.84. There's a high chance, 84% chance that I make an error if P is 3/4. So I'm going to tend, this test tends to favor concluding that there is not, right? There is not a 2/3 majority. How much time do we have? Okay. And finally, let's do for k equals 10. Although that had a pretty high type 1 bound, we have BP 3/4 was equal to probability y star less than or equal to 9 given P equals 3/4. And this is 0.61. Okay, so if I make this test is more forgiving, if I only require 10 for me to conclude the alternative hypothesis, then if I am at 3/4, okay, I would have to be 9 or fewer to make a type 2 error, and well, that can happen. Has a good chance of happening, actually 0.61, but not as high as the other ones. So the type 2 error is less. We can make a little table here, and you'll see these go together. So let's make a table here. Let's have the test be, so the test, I'll have K here, and we'll have alpha here, and we'll have P equals 3/4 here. So when K was 10, alpha was 0.181, probability of a type 1 error, and this was 0.61. Probability of a type 2 error when P is 3/4. It would change. I just picked something nominal there. If I have 11, then this is 0.84, and alpha went all the way down to 0.054, very close to what we would like. Type 2 error is pretty high here, but yeah, so unfortunately, you'd have to live with that. So we're going to ask questions like, what can we do to make these better? 12. If it's 12, well, then the probability of a type 1 error should be very small, because we're only going to reject the null hypothesis if all 12 of them say they will vote for A. And this was small. It was 0.007. And this turned out to be very big though, right? It's 0.97. So if P is 3/4, still even though very high, and chances are, at least 9 or so, 8 or 9 or 10 or 11 are going to vote that way. It's still 97% chance that not all 12 will. So that's the reason for that. So there's trade-offs. So the point is trade-off. One goes up, the other one goes down. So trade-off in the two types of errors between type 1 solution to improve both is what? Increase n. I mean, this comes at a cost though, right? Data costs. But this is the only thing really you can do. You're just squeezed by reality here, and you need more information to reduce error on both sides. You can always reduce error on one side at the expense of on the other side, vice versa, but this is the solution. Okay, so I'm going to talk about large samples tests now. This is more of the same, only we'll have a continuous distribution now, and we'll look at some more different types of tests you can do. By large sample, I mean we're going to look at cases where we have 30 or so or more, 50 or more samples to play with, and we're going to assume that our estimators are normally distributed approximately by the central limit theorem, and we will compute our type 1 and type 2 error probabilities using the normal distribution. That's all that means. So we'll look at some of these examples in the next lecture. Thank you.